Real quick, just to update your table of contents, we're on 91, we're doing biconditionals, and then on 92, we're doing commonly used arguments. So on page 91, we're going to label that biconditionals, and we're going to get down the goal. Yes? Yes?
Yes.
Okay, cool. You're going to be able to determine the true value for conditional, converse, inverse, and contrapositive statements, a throwback to your geometry days. You are hand taking these notes on page 91 about biconditionals. So when you have a statement that says if P then Q, and if Q then P, then it has its own symbol and its own name, which is the biconditional name, and then this is the symbol with the double arrow that you guys have already seen on a previous homework. That is the truth table for your biconditional statements. And biconditional basically means if and only if. So what we're going to do is we're going to look at an example, and I'm going to show you how, like, you either prove that basically the two individual statements are logically equivalent, or you can basically show that the biconditional is tautology to, kind of show this. So we're going to do one example that's going to go on this page. And all right, so for example, get down the example, don't get down the other two things that are on this page. The example is the shape is a parallelogram if and only if it has two pairs of parallel sides. Okay? These two separate statements are equivalent to each other. The first one being, if the shape is a parallelogram, then it has two pairs of parallel sides. If it has two pairs of parallel sides, then the shape is a parallelogram. Those are your two separate statements. They are equivalent to each other. Okay? If you were given a statement like this, and you were trying to determine if two statements were equivalent to each other, you could do it one of two ways. And we'll talk about those ways next, after you guys get down the example. Now with these two ways, it's more about understanding, these are the two different ways that you can do it. So I do have the steps listed. You can get down the steps in smart note way, or you can just kind of say like, okay, I think I got it. All right? So the first way to determine whether or not two statements are logically equivalent is you can write down the truth table for each of the two separate statements. Okay? Then you can compare those columns, the final columns for those truth tables, and if they're the same, then these statements are equivalent. Just like kind of what you did for your homework, right? That one homework problem. That's the first way. So you look at them individually and see if they have the same entry in that final column. So that's what we're going to do. We're going to determine if these statements here are equivalent. Okay, we're going to determine here if these statements are equivalent. So we can either do the first way, which is we create the truth table to represent this statement and then this statement separately, and then compare the two. And if they are the exact same entries, then they are going to be equivalent. So let's go ahead and let's make our truth table. I am going to do one. Doing two separate ones can kind of be a lot. Okay? Doing two can kind of be a lot. Unless you want to do two. You tell me. What do you want to do? You want to do two? No. You want to do one? Cool. All right. Break a little table. Cool. What do I need in this table? I need P. I need Q.
Not P.
I need a not P.
Not Q.
I need a not Q. I need a P and not Q.
Not P and Q.
I need a not P and Q.
And those two statements, inclusive or.
I need these two statements with the inclusive or. I don't know why this changed colors on me and then changed colors. Okay? So that takes care of the first one. And then what about the last one? P exclusive or Q. So this is it as one table. If you did it as two separate tables, you would need these first rows here for the first one, and then just P and Q and then the last one. If you do it as two separate things. Did you know this by now? How do the P's roll? How do the Q's roll? Yeah, that's right. That's you guys think you got this? Okay, I'm gonna let you complete the table. And we're trying to determine if they are equivalent. Alright, so here we go. Going down, not P.
False.
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 True. True.
Not Q.
False. True. False. True.
Now I need and between P and not Q. So that's the first column and the fourth column. False.
False.
True. P and T make true. False, false. False, true. That was comparing P and not Q. Now I'm going to do not P and Q. False, true. False, false. True, true. True, false. Now I'm going to do the inclusive or with these two columns, and I did forget my parentheses, so I'm going to go back and include them. With the inclusive or, false, false. True, false. False, true. False, false. Okay. Now so that was for this one here. I have the truth table for that. Now I'm going to figure out the column for the exclusive or with P and Q. So true, true.
False.
True, false.
True.
False, true. True. False, false. So the first way to determine whether or not they are equivalent is you can look at these last two columns, and if they are identical, then they're going to be equivalent. Okay? So yes, this is equivalent. Their two columns between those two statements are identical. So identical columns equal equivalent statements. All right? That's the first way. The second way is you can write down the truth table for the two statements with an extra column for the biconditional. Complete the truth table, including the biconditional column, and if the biconditional shows a tautology, then the statements are equivalent. Okay? That is the other way you can determine if statements are equivalent. You can look at the biconditional. Okay? You can look at the biconditional. So that's what we're going to do. Okay? And one thing you'll kind of notice too is that last table was pretty long, right? With the biconditional, it could be just the same length, but you just add in one additional column. Okay? So this is the same example that we just did. I'm just going to copy over what we had before, and if you want, you can just add on an extra column to your table that you already have. Okay? Because really, you're doing the same thing. This one was FTTF. This was the same? Yes? Okay. So now if I look at the biconditional says that if they're both true, it's true, and if they're both false, it's true. Okay? So, for this statement right here, false, false, true, 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 false, false. So this is a tautology. So because it's a tautology, they are equivalent. And like I answered before, it's your choice. It's your choice. You can kind of base off of kind of the work you've already done, or you can create your own column with the biconditional and do it that way.
Tautology.
What the other one?
Valid and then biconditional.
Not biconditional.
I mean, dang it.
All right.
Biconditional.
Here's your foldable to go on page 92. Your foldable to go on page 92. Go ahead and you're going to be cutting along the dotted line, and you're only folding on the vertical solid line. Remember, page 92 is labeled commonly used arguments. Page 92 is going to be titled commonly used arguments. This foldable is going to represent those commonly used arguments. So on this foldable, you're going to put the three commonly used arguments with their symbolic notation and what they represent. So when you have your basic conditional statement, which is your implication, P implies Q, then you have these other three commonly used arguments, which are the converse, the inverse, and the contrapositive. Q implies P is the converse, not P implies not Q is the inverse, and not Q implies not P is the contrapositive of the original statement. So, you'll be able to recognize these here. Okay? So, again, this is based off of the original conditional statement here, and then you flip from there. Okay? So, I'm just flipping P and Q, or I'm flipping the antecedent and the consequent, and then I'm negating them, and then I'm flipping and negating. Okay? Just like how you did back in geometry. All right? Now, we're going to do some examples just so you guys can practice writing these different sentences, and that's what's going to go on the lines of your notebook, or, you know, if you got it, they all got to go on page 92. You got to figure it out, like your example. So, we're going to find the converse, inverse, and contrapositives of the argument is if the weather is sunny, then I will go for a swim. If the weather is sunny, then I will go for a swim. Now, the one thing I definitely don't want you guys to do is just to start writing sentences and you don't identify what they are, okay? Make sure you identify which is which. So, make sure you write out converse, inverse, and contrapositive, so then that way the grader can also know which one you're trying to refer to, and not just saying, okay, I'm going to put all these statements up here and then, you know, hope for the best. No, identify what they are. Converse says you're going to switch your consequent and your antecedent, okay? So the part that follows the if and the then, they switch places. So the converse is going to say what? If I go for a swim, then the weather is sunny. What would be the inverse?
If the weather is not sunny, I will not go for swimming. Or go for swimming.
There you go. If the weather is not sunny, then I will not go for swimming. And the contrapositive? Beautiful. If I don't go for a swim, then the weather is not sunny. Woo! A lot of writing. But it's all good. Okay? We get those easy points, gimme points, as long as we go based off of that. Okay? Questions on writing the sentences? Awesome. Okay. Now, do not write down this table. Okay? Let's just take a look. This table summarizes the truth value for the direct argument P implies Q, and then the other conditional statements. Okay? You have the converse here, you have the inverse, and then you have the contrapositive here. Okay? Notice anything?
The converse and the inverse are the same.
Converse and the inverse are the same, and the original and the contrapositive are the same? Yes. Okay? The converse and the inverse are always equivalent, and the original argument and the contrapositive are always equivalent. Okay? Don't forget about it. Okay, don't forget that. Could very well happen that they ask you a question and ask you to determine which one of these statements are equivalent, and instead of doing the truth table, could save you some time if you just memorize those. Okay. We're gonna look at another example, but I think you guys get the idea of writing the converse, inverse, and contrapositive. So then we're just gonna talk about this next example. Okay. Still recording, right? Blue dot. Blue dot. Okay. Ready? All right. We're not writing this down. We are just talking it out. So, if it is raining, then the streets are wet. Who has the converse for me loudly? Who has it? The converse.
If the streets are wet, then it's raining.
If the streets are wet, then it is raining. Beautiful. What about the inverse? So indifferent. Yes.
If it is not raining, the streets are not wet.
If it is not raining, the streets are not wet. Beautiful. And the contrapositive one. That's one. Yes.
If it is not wet, then it is not raining.
What is it?
If the streets are not wet, then it is not raining.
If the streets are not wet, then it is not raining. Beautiful. Okay? Let's look at this one here. Still going to talk it out. Okay? Get a little bit of math going. If the final digit of an integer is 0, then the integer is divisible by 5. We're going to find the contrapositive, the converse, and the inverse. You see why you have to make sure you list it? Because they changed the order up on you. So if you just start listing in order of converse, inverse, contrapositive, then how are we going to know which is which, right? Okay? So indifferent. What's the contrapositive to the statement? Was that a contrapositive or was that the converse? That was the converse. But you were right about the converse. You said if the integer is divisible by 5, then the final digit of an integer is 0. Very good. Inverse. So indifferent. Shy. Only a handful of y'all. You already know. Let me call you out on this video. Summer, give me the inverse.
If the final, If the final digit of an integer is not 0, then the integer is not divisible by 5.
Very good. If the final digit of an integer is not 0, then the integer is not divisible by 5. And then the contrapositive.
If the integer is not divisible by 5, then the final digit of an integer is not 0.
Very good. If the integer is not divisible by 5, then the final digit of an integer is not 0. Very good. Very good. You guys have a strong handle on this, yes? Awesome. Real quick before we finish up, a counterexample is an example that makes the statement false. Okay? This is a throwback to geometry. Okay? But a counterexample is an example that makes the statement false. So for that last example that we were talking about, if the final digit of an integer is 0, then it is divisible by 5. Can anyone think of a counterexample for that last example?
0.
0. Okay? So, a counterexample is something that makes it false. So, if the final digit of an integer is 0, so it has to end in 0, then it has to be divisible by 5. The only thing that will work would be 0 itself. Here's another one. If x squared equals 1, then x equals 1. Can anybody come up with a counterexample for that? Say what? -1. A counterexample would be -1. Think about what's -1 squared? 1, right? -1. All right. Did you guys understand counterexamples? Make sense? Cool. All right. Now this is just like I have not seen anything in the last 5 years of them talking about this or kind of like trying to trick you here, but it's better that I say it than I don't say it. But it's often the case that given a valid argument, its converse is not valid. Okay, this is known as the fallacy of the converse. Now, will that happen to you? I've yet to see that happen, but I'm just putting that out there just so that you guys, you know. Okay. But yeah, that's logic. That was the end of logic there. Okay.